momentum, okay, is we will focus. I will explain you on force acting on control volume and linear momentum equation. Okay, in terms of force acting of control volume, so in our control volume, we will have two types of force. One is body force, another is surface force. In terms of body force, normally you will have the effects of gravity, the effect of electric, the effect of magnetic. In terms of surface force, you will have a pressure force, viscous force, and reaction force at the point of contact. Okay, this is clearer condition. You can see it. For example, this is your control volume. Inside is a control volume. Then you will have a control surface at the surface. Okay, so control surface happen at this surface of the control volume. So this is your control volume. For example, the gravity effects, electrical effect, magnetic effects. The surface is more on surface on that control volume. So the total force acting on the control volume is composed by a body force and also surface force. Body force is the differential volume of the element, and the surface force is differential surface of the surface element. Okay, the formula of total force is addition of total force of body force plus total force of surface force. So which shows that the force acting on control volume consists of body force, which is entire of the control volume, such as gravity, and the surface force at the surface, such as pressure force, viscous force, and reaction force. So this is the total formula of force. Okay, the most common control volume, body force for control volume is gravity force. So normally gravity force is one of the most commonly used. Okay, so which exerted downwards to the force and on every differential element of control volume, while the other force, like electrical, magnetic, is important, but is based on condition. We will consider normally the most important, that we will consider of gravitation force, because everything should have a weight. So the gravitation force, we know that this is the formula of gravitation force, which is differentiation of force gravity is equal to rho g differentiation of volume. So or rho gv, and change of volume, rho gv is become the gravitation of force. Okay, this is example of gravitation force, a body's force of gravitation force acting on different volume. So you can see here. Okay, if you can see here, okay, we will have the third session to finish it. Okay, we will notice here the gravity effects is going down. So the body force of gravity is rho gv, but the direction towards down. So this is the effect of the volume, the control volume of body force. Okay, in terms of surface force, is the formula is differentiation of sigma ij dot n dot, means it consists of sigma, mostly a shear force, shear acting on that particular surface. So it consists of both normal and tangential component, which is the physical force acting on the face is independent on orientation of coordinate of axis. The description of force in terms of its coordinate component change with orientation. So so if you can see this one, this is a better explanation of surface force. If you can see here, the axis of x and y become something like this. So when this is your surface, so that the surface force acting towards the normal of x and y. So if the direction is x and y, the first, for the condition of A, automatically we know that this is for this one, this is the normal tangent force, and this one is summation of on x surface of direction of surface force. But if we rotate these things in some angle, so your x and y is not it's a little bit rotate, something like this, so automatically your normal become following the y-axis and your x will following the new x-axis. So means that if you have a force of the surface force here, and also you have a surface force here, you have A and also B, the for example xy is the same, y is x, so your resultant force will be different because this one is following x and y, for example. So it depends on the rotation, the location of the surface. Okay, so in this case your resultant become something like this, but for the second B, due to your x and y change, the direction of resultant will be based on your x and y axis. So if you have condition A, it's not the same like condition B. Okay, so that's why it shows that surface force, it depends on the surface area and also axis. Okay, in term of stress tensor in Chapter6 coordinate, if this is the shear force diagonal of matrix, in this one, if you have this type of force magnitude, we know that diagonal component of the stress tensor are called normal stress. Means that this diagonal x, x, y and z, we call it as a normal stress. Okay, which is composed of pressure which acting inward, normal and viscous stress. The off diagonal component are called shear stress, since pressure acting only normal to a surface, shear are exposed entirely viscous area. Okay, the other part is we call it as a shear stress. I think you have learned this one in your finite element, not finite element, static, I think. Or you, okay, so means that if you have x, y, y and sigma z, z is a normal force, the rest become shear force. Okay. Okay, this is the component, the example of, like I said previously, the direction will be changed based on, for example, the first y, sigma y here, sigma xy, sigma yz. So your x, y, z, each of the surface will have different calculation based on the condition. Okay. Okay. So here the total body force acting on control volume is rho GV, and the total surface force is based on sigma times n. Okay. So the total force is addition of total body force and surface force. So the formula is differentiation and integration of control volume rho GV, okay, the changes of each volume calculation, plus the integration of control surface of sigma ij, which is your stress tensor, with your direction of normal in terms of area. So this is the main formula of total force. Okay. Okay. To be more details, this is your formula of total force, which is body force plus pressure force, which is surface force in terms of pressure force, viscous force and other force. As we mentioned previously, normally for body force, we just consider for the gravity force. That's why the summation of gravity is only here as represent of body force. But in terms of surface force, there will be a pressure force, viscous force, and other force. So the first term of the right side is a body force weight, since the gravity is only considered, yes, for body force. And for the surface force, we should consider pressure, viscosity, and other force. This is your final formula of total force. Okay. So one thing you need to understand that a common simplification of application Newton's law of motion is to subtract to atmospheric pressure and work in the gauge pressure. So this is because atmospheric pressure act in all direction, okay, and it effects cancel out in every direction. This means we can also ignore the pressure force at outlet section where the fluid is discharged to atmospheric, since the discharge pressure in such a case will be very near atmospheric pressure subsonic velocity. So for example, with atmospheric pressure considered, we can say that pressure of inlet and outlet, for example, there is atmospheric, so it's almost the same. So what in should have the resultant action. But with atmospheric pressure cancel out, means that we are this, for example, the pressure is inside the pipe. We are not assuming no of the outlet of atmospheric pressure. So means that the atmospheric pressure should be eliminated. We can easily focus on the effects of the inlet and also the weight. But if atmospheric means that something like this lah. If the pipe is open, okay, if you have an open pipe, open to atmospheric, I think you in the second chapter we learn, automatically we can assume this is PATM is equal to 0. For example, this one is not a PATM, this is the outlet. So if you have a flow here, the outlet is here, inlet here. What we do, we take the control volume inside here. Means that when you take out this one, your fluid won't have a PATM effect. So that's why your calculation will be, you cannot assume this here is PATM. So this is wrong because of you are taking this area. But if you are taking totally the nozzle outside, you can take it, PATM is 0. So that's why for a PATM 0, it will be neglect due to PATM 0. But if you take the control volume inside of the pipe, not opening towards atmospherics, you cannot assume the outlet here is a PATM. It should be a pressure, inlet pressure, different pressure here and also here. You cannot take it as, we take it, this is an example of control volume inside the pipe, but here is towards the, what we call it, the tap, okay, the tap of the pipe. So control volume of B, so you will have two types of control volume here. First is control volume inside of the pipe, okay, as a control volume A. So this is the flow acting inside of the pipe. And you also have a control volume of B, which is control volume of B, which is the area of the tap pipe. Okay, control volume of B is wisely choice because first is not concerned with any details of the flow or even the geometry inside the control volume. So means that if you take control volume of A, your area will be effects on this all the detail of inside here. But we want to know the answer of the outlet and inlet, for example. So instead of you are taking the control volume very detailed here, it's better for you to make it a bigger control volume, because we assume this will be the flow inside here is directly outside here. So not all the small detail can be ignored in terms of the calculation. Okay, So that's why control volume B is better to take rather than taking control volume of A. So one of it is because of the detail flow or even the geometry inside the control volume is much difficult compared than the control volume B. Second is only need to know the gauge pressure of the water at the flange, the inlet of the control. We just want to know the inlet, and the weight of the water at the faucet assembly, the weight of the total water inside. Okay. Okay, the third is pressure everywhere else along the control volume is atmospheric gauge pressure and cancel it out. Okay, so means the cross section through a faucet assembly illustration the importance of choosing a control volume. Control volume B is much easier to use compared to control volume of A. One of it is, if you take it A, so automatically your control volume, one is because of all these difficulties of details. Secondly is, this we cannot assume this as a atmospherics, for example, so because inside. But when you take it outside, means that control volume V, automatically in this area become atmospherics and this area become not atmospheric. So automatically you can cancel it out. You can assume P ATM equal to 0. So it's much easier to calculate compare than you just focus the detail here. So that's why choosing a control volume is very important. For example, previously, if you remember, we have the hose, something hose here, then we have jet flow here. If you remember, we take the control volume is here directly. Why? Easier to calculate because here is automatically we know this P ATM. But we are not taking the control volume here. For example here, this is much difficult to calculate, or inside here, and inside all this inside is much difficult because in terms of calculation, for example, you have a Bernoulli equation, okay, rho G plus Gz is equal to P2, for example, okay. So automatically, if here is P2 P ATM, we take the first control volume, we can cancel it as 0. But if you are not taking the correct one, it's much difficult. We take inside, you have your own pressure here, the calculation will be much difficult, because at the end of the day, we just want to know the result of this area normally. So that's why selecting control volume is very important. Okay. Okay, so this is the last. Okay, next is linear momentum equation. Okay, Newton's second law for a system of mass subjected to net force is expressed as F equal ma, or m differentiation of velocity towards time, or differentiation of mv vector. Okay. So we know that mv is the linear momentum of the system. So noting that the density and velocity may change from point to point without system, Newton's second law can be expressed as differentiation of time of rho v volume. Okay, means that rho dv is the mass of differentiation volume element of dv, and rho v dv is in momentum. So Newton's second law can be stated as the sum of all external force acting on the system is equal to the time rate of change of momentum systems. So shows that the statement is valid for coordinate system that is rest or move with constant velocity. We call it as initial coordinate system or initial reference frame. So the acceleration such as aircraft during takeoff are best analyzed using non-inertial or acceleration coordinate system fixed to the aircraft. So means that in momentum equation, we can simplify it from this one to become the summation of rho v dv. Then this is can be analyzed using non-linear initial or acceleration coordinate.